So this video is still on the course of representation theory, and we are on the chapter of representations. But now I made some revision, some linear algebra revision at the beginning, the first couple of videos, but I need further linear algebra revision here. So I just want to recheck the concept of orthogonal matrix. This software does these strange things. It's hard to make a line here. Okay, what is a orthogonal matrix? If the transpose equals the inverse, we say the matrix is orthogonal. So if you have a matrix A, you take the transpose and you see that the inverse equals the transpose, so A is orthogonal. Okay? Now I wrote it this way here too, because this is the same principle, right? If you right multiply, so A transpose times A equals A inverse times A, and A inverse times A is the identity, right? So here you are, okay? A transpose times A equals the identity. So when A transpose times A equals the identity, this is A is an orthogonal matrix, okay? And you can do the same for the left, okay? And you will get A times transpose equals the identity, okay? So this is a orthogonal matrix. Now, some characteristics of orthogonal matrices. Since the definition of orthogonal is that the transpose equals the inverse, so the matrix has to be invertible, right? Otherwise it can't be orthogonal. On the top of it, it has to be unitary, meaning that the inverse has to be equal to, I'm going to use this symbol for unitary. Okay. What is a unitary matrix? I'm going to use the word, I'm going to call the matrix U to call it unitary. A unitary matrix is a matrix that it is equal to its transpose conjugate, okay? Conjugate transpose or transpose conjugate, okay? This matrix is called a unitary matrix, okay? So the analog for this, the real analog, this is an imaginary matrix, right, with complex entries. The real analog for this is the orthogonal matrix, okay? So they are somehow linked. Okay, I said invertible, unitary. I forgot to say the matrix has to be also normal. Okay, so normal means A equals A. This is a normal matrix. Okay, so another aspect, the determinant of a orthogonal matrix, it will be either plus or minus 1, okay? Otherwise, if the determinant is not plus or minus 1, the matrix is not orthogonal. Okay, some other characteristics. As a linear transformation, do not forget that a matrix is a linear transformation. As a linear transformation, a orthogonal matrix preserves, I'm going to write this, it preserves the dot product. So some linear transformations, they preserve the angle of vectors, some other they preserve the length of the vector, etc. So orthogonal matrices, they preserve the dot product. So if you have a given dot product, okay, under a orthogonal matrix, the dot product is preserved. So if you are in a Euclidean, if you are in a Euclidean space, this orthogonal matrix will act as a isometry. Okay, so acts as an isometry on an Euclidean space. Examples of isometries: a rotation, okay, or a reflection. Okay, these are isometries. Okay, so in other words, this orthogonal matrix is a unitary transformation, if you prefer. Okay, these orthogonal matrices, they, of course, they are square matrices. Okay, so they are n by n orthogonal matrices. Okay, they form a group called the orthogonal group, ON, the very famous ON. This appears a lot in physics and other stuff. Okay, so this is the orthogonal group, a very important group. Okay, as I said, the orthogonal group, the orthogonal matrices, they have determinant 1 or -1, but this orthogonal group has a very special subgroup called the special, I'm going to write it, called the special orthogonal group. So this special orthogonal group, it's a subgroup of the orthogonal group, consists of all orthogonal matrices too, like this one, but the determinant of these ones has to be 1. Okay, so this one is called the special orthogonal group. So as a linear transformation, every special orthogonal matrix acts as a rotation. Okay, so all from the linear transformation point of view, all these matrices, they are rotations. This is very important with lots of applications to geometry.